Hi everyone. Today I'm going to talk about Cheeger inequalities for directed graphs and hypergraphs using reweighted eigenvalues. So let's start with the classical Cheeger's inequality. Given an undirected graph G, the conductance of a graph is the minimum ratio between the number of edges crossing the cut S and the total degree of S. So we take the minimum over all vertex subsets S. So this is a measurement of how well connected the graph is, and our task is to either find a cut S with small phi or certify that all cuts have big phi. Cheeger's inequality is a fundamental result in spectral graph theory. It connects conductance with the second smallest eigenvalue of the normalized Laplacian, I minus script A, where A is the normalized adjacency. So this theorem dates back to 70s and 80s, and essentially it says that conductance is small if and only if lambda 2 is small. So that means lambda 2 can be used to certify conductance. And what's nice about this is that by examining the second eigenvector of the Laplacian, we can extract a cut with small conductance. So applications of Cheeger's inequality include graph partitioning, solving linear systems, divide and conquer, analyzing mixing time, and so on. So these practical uses stem from the fact that eigenvalues and eigenvectors are easy to compute. More recently, using other eigenvalues and other combinatorial parameters of the graph, people were able to derive generalizations of Cheeger's inequality. And the bottom line is that this is a rich theory. Another appealing feature of this spectral theory is its connection to mixing time of random walks on graphs. So if the graph is unweighted, then the canonical random walk simply picks a random neighbor of the current vertex and go there. So one well-known fact is that the mixing time of this random walk is roughly proportional to 1 over lambda 2. And by Cheeger's inequality, that means conductance, small conductance, is the only obstacle to a fast mixing time. So to summarize, the classical Cheeger's inequality connects conductance, eigenvalues, and mixing time, and also has generalizations to other eigenvalues on the spectrum. So that's the background. And now let's talk about reweighted eigenvalues, which is a fairly recent concept. So to motivate reweighting, consider the following graph. So you have two copies of the n-node complete graph, one on the left, one on the right, and you connect them using a perfect matching. So assuming that the edge weights are uniform, the mixing time would be theta n, because for example, it would take roughly n steps for you to cross from one side to the other. So suppose you want to make the mixing time faster. What could you do? Well, one way is to increase the weight of the matching edges, let's say from 1 to n. So if we do that, and if we take each random walk step in proportion to the edge weight, then now there's a constant probability of crossing to the other side. And in fact, we can show that the mixing time is constant. So basically, that's the premise of the fastest mixing Markov chain by Boyd, Diaconis, and Xiao in 2004. So basically, given a graph, they're looking for a Markov chain supported on the edges of the graph so that the mixing time is minimized. Well, but mixing time is not something that is easy to optimize for. So the idea is to use eigenvalue as a proxy for mixing time. So instead of minimizing mixing time, they minimize the second eigenvalue of I minus the transition matrix. So that's the following program. We're maximizing lambda 2 of I minus p. And the constraints, the first one says that the walk is supported on the edge set. Second one says that row sum should be equal to 1, so there's a walk. And the third one said that p is pi reversible, so that it corresponds to reweighting the edges. Okay, let's take a slight detour and talk about vertex expansion. So given an undirected graph, G, vertex expansion is the minimum ratio between the number of neighbors of a subset S and the size of S. We can also define a pi-weighted version if we're given any distribution of weights on the vertices. So a priori, it's not clear what reweighted eigenvalue has to do with vertex expansion. In 2005, Brock proved that lambda 2 star is less than psi, but since then, basically development of this connection has stalled for quite a while. And in 2021, Oleska, Taylor, and Zanetti proved a Cheeger-like inequality relating vertex expansion and reweighted eigenvalues, which was subsequently improved to its current optimal form by Kwok, Lau, and Tung. They also proved relations between other reweighted eigenvalues and other vertex expansion qualities analogous to the generalizations in the edge case. So this is all nice, and following their work, one natural question would be, can we develop a spectral theory for directed graphs and hypergraphs using reweighted eigenvalues? And this is the central question that our work sets out to answer. So before talking about results, one helpful viewpoint would be to regard the reweighted subgraphs as certificates of expansion. So in the case of vertex expansion, we're looking for a Markov chain P, but then if we consider the matrix Q, which is pi p, then it corresponds to giving the weight pi I times pij to the edge ij. If we do it like this, then the weighted degree of vertex I in the reweighted subgraph Q will be exactly pi of I. And one observation is that the total edge weight crossing S and its complement must be at most the total pi weight of the set of neighbors of S. So for example, in the figure, the sum of edge weights of the orange edges would be at most pi of x, and the edge weight of the blue edge would be at most pi of y. So like these are like reweighted edge weights. Well, but phi q is not computable in polytime. So we use classical Cheeger's inequality to lower bound phi q by lambda 2 of the normalized Laplacian, which is computable. And we're optimizing over all these reweightings Q. We're trying to maximize lambda 2. So basically the message here is that lambda 2 star is a polytime computable proxy for phi star, the best reweighting to lower bound psi of G. Okay, with this in mind, Now we're ready to talk about our results. Now we define the directed combinatorial quantities of interest. So the directed edge conductance is the minimum ratio of two things. In the numerator is the edge weight from S to its complement, and the edge weights from the complement back to itself. So we take these two things and take the minimum. Whereas in the denominator, it's just the sum of weighted in degrees and out degrees of S. Directed vertex expansion is defined similarly. In the numerator is the minimum pi weight of the out neighbors of S and the out neighbors of S complement. And in the denominator is just the pi weight of S. So one immediate obstacle that you'll face if you try to derive a spectral theory for directed graphs is the associated matrices are not symmetric. So the adjacency matrix, the Laplacian matrix, they may not be symmetric at all and may have complex eigenvalues. Nevertheless, there have been considerable past attempts on developing such a theory. For example, Fu and Chuen, they defined this Cheeger constant and derived a Cheeger inequality for it. And Yoshida derived a Cheeger inequality for nonlinear Laplacian. So of course this list is not exhaustive. So our idea is to do something similar to reweighted eigenvalues for vertex expansion. So that means we want to look for certificates for expansion. We want to find a class of reweighted subgraphs that could, so that its conductance could lower bound the expansion quantity that we're interested in. Moreover, we want the certificates to be computable. So with this in mind, the idea that we came up with is to consider Eulerian reweightings. So recall that a directed graph is Eulerian if and only if at every vertex the in degree is the same as the out degree. So in the case of edge conductance, we will consider Eulerian reweightings that satisfy edge capacity constraints. That means each edge in the reweighted graph would have a weight that is less than or equal to the original edge weight. So with this being the constraints, then there are two reasons why Eulerian reweightings would be the way to go. First of all, conductance of the reweighted graph is a lower bound on the original conductance. And it's simply because the amount of edge weights going between S and S complements can only go lower. And the second, more important reason is, for an Eulerian graph, you can basically consider its undirected counterpart, which is you forget all the directions of the edges. And basically, this operation wouldn't really affect the conductance of the graph. So that's how we arrived at this reweighted eigenvalue for directed graphs. So for the edge-weighted case, we have this lambda 2 E star. So we're maximizing a Laplacian. Here is A plus A transpose over 2 because A is the Eulerian reweighting, and A plus A transpose divided by 2 is the undirection operation, so to speak. And the constraints are pretty simple. First one says that A should be supported on the edge set E. The second constraint said it basically the Eulerian constraint at the vertex U. And the last one is the edge capacity constraints. So for the vertex weighted case, we consider lambda 2 phi star, which is basically the same thing, except that edge capacity constraints becomes vertex capacity constraints. So our main results are two Cheeger inequalities, one connecting the directed edge conductance and lambda 2 E star. So basically it looks quite a bit like the classical Cheeger's inequality, except that there's an extra log of 1 over lambda 2 term. And the second theorem connects the directed vertex expansion with lambda 2 V star. And this time the log term becomes log delta over lambda 2 V star. Delta here is the maximum combinatorial degree of the graph. So here are some consequences of the Cheeger theory. So the first one is extracting Cheeger cuts. In fact, the proof of these Cheeger inequalities are again constructive. So by solving the SDP and finding a rounding algorithm, we can actually compute sparse cuts with these Cheeger type guarantees in the time you need to solve the SDP. And the second consequence is that you can certify constant directed edge conductance using lambda 2 E star. So from the Cheeger inequality presented, you can note that phi is constant if and only if lambda 2 E star is constant. So it's very nice. And the last application would be fastest mixing Markov chain on directed graphs. So we're looking for general Markov chains with a prescribed stationary distribution pi. And it turns out that we have fastest mixing if and only if psi is large. So basically this looks quite like the relation between fastest mixing reversible Markov chain and undirected vertex expansion, but there's some extra log terms here and there. In terms of the generalizations, unfortunately, we discovered that the bipartite Cheeger inequality and the higher order Cheeger inequality do not extend naturally to the directed settings. But in fact, the improved Cheeger inequality that upper bounds conductance with both lambda 2 and lambda k has a directed analog. And you can refer to the paper for more details. So we mentioned that we also managed to derive a reweighted eigenvalue theory for hypergraphs. So basically it's the same spirit. We're looking for a polytime computable certificate for hypergraph expansion. And the way we do it is to consider the clique graph. So for each hyperedge, we just take all its vertices and then add a clique connecting all of them. And then we consider reweighting the clique graph, and we use the conductance of the reweighting to certify conductance of the hypergraph. So by this idea, we managed to recover and improve some results of Lewis and his co-authors. Okay, next I'm gonna talk a little bit about the rounding algorithm. Just want to give you a broad outline of it. For the outline, we'll consider lambda 2 E star, so for the edge conductance. By combining the Rayleigh quotient characterization of eigenvalues and von Neumann minimax, we can write the lambda 2 E star program in this min-max form, where the minimizer is over vertex embeddings F, and the maximizer is just looking for maximum Eulerian reweighting. So after writing the lambda 2 E star program in this form, what we're going to do next would be to project the high dimension embedding to a one-dimension embedding. So to capture this dimensionality of the embedding, we will define lambda e of k to be basically the same min-max program, subject to the same set of constraints on A and on F, except that now F will be a k-dimension embedding. So k can vary from 1 to n or even beyond. And what we would like to do is to project the original n-dimensional solution to a one-dimensional solution. So that means a solution for lambda e of 1. So to argue about the quality of the projection, we derive what we call the large optimal property. So it basically says that if the original graph can be covered by m reweightings, covered here means that if you add up the edge weights of the reweightings, it will be at least the edge weight in the original graph. So suppose m reweightings is enough to cover the original graph, then random projection loses a factor of log of some constant times m. So that means the task now is to propound m for directed graphs. So let's derive some intuition by considering extreme cases. If G is Eulerian, then m is 1 because you can just take G to cover G itself. Whereas if G has a very unbalanced cut, so for example, if there's a lot of edge weight going from S to S complement, but very little going from S complement to S, then in every reweighting, there would also be very little edge weight going from S to S complement. That means you need a lot of reweightings to cover all of these edges from S to S complement. So that means if G is somehow like very unbalanced, then M should be large. So let's quantify this. Define asymmetric ratio as alpha, which is the maximum ratio between the edge weight from S to S complement and to the edge weights from S complement to S. So we take maximum this time. So by applying Hoffman's circulation lemma, we can actually show that the number of reweightings we need is O of alpha for directed edge conductance. Moreover, we can upper bound alpha by 1 over lambda 2 E star. So that means by the large optimal property, the projection loss is bounded by log of 1 over lambda 2 E star. So these will explain the respective log factors in the Cheeger inequalities for different settings. Because for these different settings, we can derive different upper bounds on the number of reweightings needed. So after projecting to one dimension, the next step is to consider the L1 program. So the L1 program, we call it nu E of G. It's basically the same as the one-dimensional program lambda E1. So the differences are only in the objective, where the squared norm, the squared L2 norm now becomes an L1 norm, and also the normalization becomes an L1 normalization. So we can prove that there's a square root loss between these two quantities, and it's by constructing L1 solutions from L2 solutions. And finally, we arrive at the most familiar step of any Cheeger proof, which is the threshold rounding. So basically, we just take the dual of the one-dimensional L1 program And then given a feasible solution, f and r, to this program with objective value given, then we can use threshold rounding to obtain a cut whose conductance is upper bounded by a constant times the objective. So in like previous threshold rounding algorithms, they will usually consider either the positive part or the negative part of the embedding f. And here, the tweak is that we have to consider the positive or negative part of either f plus r or f minus r. So one of these will succeed. So to summarize, we start with the reweighted eigenvalue formulation. We use Rayleigh quotient and minimax to derive an n-dimensional program. We use large optimal property to control the projection loss to the one-dimensional program. And then we go from squared L2 objective to L1 objective, which is then amenable to threshold rounding. Okay, so let's wrap up here. So basically, the takeaway is that this work develops a spectral theory for directed graphs and hypergraphs based on Euler reweighting. And I would say that this is actually a unified theory for all graph or hypergraph settings, because essentially the idea of reweighting is to reduce these new difficult to tackle settings to the classical theory for edge conductance, for which computation would be easy. So we're also pretty excited to see further developments on this reweighted eigenvalue theory. So right now, what we have developed is kind of like a groundwork, a theoretical foundation for this theory, reasons why it's good. But then we hope to see more applications, for example, theories where you can tackle using just normal eigenvalues previously. What if you apply reweighted eigenvalues? Maybe there'll be something new. And let me end with some open questions related to our work. So the first question is how to formulate bipartite or higher order Cheeger for directed graphs. So we already know that the natural formulation wouldn't work. And second question, are the log terms in the Cheeger inequalities tight? And the third question would be whether they are almost linear time algorithms to either compute these reweighted eigenvalues or extract the Cheeger cuts. And finally, especially because there's applications to hypergraphs, we're hoping to find some concrete practical applications for our work. So that's the end of the presentation. If you're going to STOC, remember to come to our STOC talk. Thank you.